Welcome to the Fundamentals of Blueprint Reading. My name is Urmaze I'm the Head of Research and Development at the Oregon Manufacturing and Innovation Center, R&D.
Blueprints were invented a generation before the Civil War by John Herschel, a chemist, astronomer, and photographer in 1842. Herschel developed the cyanotype process that started with a drawing on semi-transparent paper, weighted down on top of a sheet of paper. The paper was coated with a photosensitive chemical mixture of potassium ferrocyanogen and ferric ammonium citrate, a hazardous chemical formula. Once the drawing was exposed to light, the exposed parts turned blue, while the drawing lines blocked the coated paper from exposure and remained white. The blueprint process eliminated the cumbersome expense of hand tracing original drawings. By the 1890s, in architectural offices, a blueprint was 1/10 the cost of a hand-traced reproduction and could be copied in a fraction of the time using the photochemical process.
Let's start by going over some of the fundamental input fields of any basic blueprint. Here highlighted in blue are the typical input parameters that a designer would start with. In this case, this blueprint was submitted to us by a company named Kennametal, and they are known internationally for machining solutions and manufacturing of cutting tools for various industries, from aerospace to automotive to die and mold and many others. So one of the first most important input fields for them is going to be the drawing number. So clearly that becomes important because they need to identify this drawing out of thousands of other ones. Another very important field to them is who the designer or the drafter of this blueprint was, so that downstream, if there's an issue with the quality or the correctness of the print, they can track that individual down and make the corrections. In some companies, they have a very high quota of designers and drafters, so they want to know which of them are more efficient and reward them accordingly. So that's another reason why this becomes really important. Almost all designs are checked by either the supervisor and approved by them, so that becomes really important. Dates are always relevant, and then of course the scale of the drawings is identified. Another really important field here is the sheets. So just because we're looking at the front sheet doesn't mean that that's all there is to it. Occasionally a design is so complex that you may want to look at multiple sheets. So you should always check for that, because that can help you or hurt you in manufacturing. Very important to note the version number of the drawing. In this case, it's the very first version or the 00 version, and so there's no issue. Occasionally, people in a factory will print out a blueprint and take it over to a machine or an instrument, and it can sit there for years. And what happens is the designer may have improved the design or changed the material type or any adjustment, and that's then maintained in the computer records, but the people on the manufacturing floor are still following a former version. So that is one of the reasons a lot of manufacturing factories have moved towards digital blueprints, and they're located right at the machines nowadays. But it's always good whenever you're looking at a printed version to confirm that you have the correct version. Still continuing to talk about the template of the blueprint, and this next box in the red border, sorry, is going to talk a little bit more about the components and the parts. And the way we describe that is with this DET number, or often referred to as the detail number. So in this particular coolant plug design, there are basically two components, number 1 and number 2, and they're identified over here by these balloons 1 and 2. And 1 is known as the brass body, and the number 2 is the O-ring. And so those are two components being put together or assembled there. We have a quantity of 1 each. and they are included or are required. And that's just information towards the eventual customer. And then also it's really important to identify the part numbers. And you should observe that these part numbers are several digits long, so that this reflects on the volume of parts that this company has in their catalog. So it becomes really important that they identify the correct numbers on these drawings. Next, we will talk a little bit more about data that the Kennametal company wanted to provide towards its customers, and this reflects the correct utility of this component, and they provide that on this print by way of notes. So they identify that the maximum pressure that this coolant plug can accommodate is about 1,500 psi. It's made out of brass. They want to follow the best practice of tightening it to 60 inch-pounds of torque. Basically, this plug is assembled onto a cutting tool body so that cooling fluids are provided to it through the machine while it's cutting. And then a caution that they do not want to over tighten this component. And lastly, highlighted in this orange field, the company wants to provide a little more details on some that are more manufacturing related. I think that's a little bit outside the scope of this workshop, but I'll just let you know that it has to do with some surface finish requirements during machining and ISO published specs that they are required to put. It's almost like a legal requirement that these companies can put. And if somebody chooses to go deep into becoming a specialist on design and making blueprints, then that would be a good time to deep dive and learn this. But for now, I'm going to focus a little bit high level so that you can learn how to read a blueprint and make it fun, and also be able to create some basic blueprints that you can use in your daily lives. And before we move on, just so you can have an appreciation for what modern manufacturers go through in terms of details, the blueprint of the coolant plug we just talked about, that's this component on this modern day cutting tool. This is known as an indexable cutting tool, and coolant comes out of these ports, and they are able to control the pressure and the volume of coolant that can come out, or even block it off by using these things known as coolant plugs. So much detail goes into even the blueprint of a small little component. Now, of course, in modern day blueprint making, of course, they're no longer blue, they're just basically usually black and white. But it all starts with a design in a computer system where the designer will draw a 3D rendition of what they're trying to manufacture. And in this case, I drew up a simple CAD design which looks like this. And I'm going to try and bring it into a blueprint template. And usually what happens is that we would first create two views of this thing. And here we'd have the top view and then the side view. And in this case, I've just color coded them orange and blue just to help you with visualization, but it's actually one piece. And I'd like to draw your attention to is that in the 3D model, you may not have observed that the holes are going through and through the part. And additionally, we have two different types of holes. So in the orange component, we have a larger hole identified by the dotted lines. And then in the blue part, blue section, I should say, is a smaller hole. That would not have been self-evident in this 3D model. So the blueprint really breaks it down by the orientations, and there's all kinds of complexities we can add to the design. It's important to note that in today's design and manufacturing world, the engineers or the designers, they would just using CAD systems just draw up what they need to make, and then the computer can really quickly create these various views and orientations and get it ready within a set template for dimensioning and additional details. So now I'm going to start by bringing in my design into the blueprint template. And of course, this is generic, it's just for teaching it. I always start by inputting some of the key basic parameters of the part number and the author and who it's for, and drawing numbers and versions and so on. And next, the computer will auto-generate the top and side views, and by way of the hidden lines and the center lines, I'm able to provide a little more details on what my expectations are for holes that are through these two sections of this design. And next, I can give the reader some more dimensions on each of these features. So now we want to confirm that we have enough details so that we can manufacture this part. So I'm going to highlight the sections here. The orange section has an outside diameter of 2 inch and a hole within it of 1 inch, whereas the blue section has an outside diameter of 1.25 inches and a hole within it of 1/2 inch. And it should be pointed out that I'm further giving some more details in the lower print here by saying that I want these holes to specifically be drilled out, and also I want them to be on the center line of the part. And these are more details that we provide to manufacturers to control things like concentricity and runout. So, and it's always good to check if there is any dimension that's been missing. Here I also provide the length of each of the components of 1.75 inches and 1.5 inches. And it's important to point out that as compared to this 3D model, I have scaled my views to 3/4:1 inch. And then finally, I'm giving the reader a little more detail on the manufacturing of this part up here in my note by letting you know that I want it made out of material 4340 steel at about 30 to 32 Rockwell. I'm also just making sure that anybody who sees this understands that the colors shown are for visual ease only, and the part is actually made from one integral piece of material. And lastly, as you have been viewing these images, you may have observed all kinds of lines on these blueprints. So at least these are some of the ones that are important to know at a beginner's level and not to use them interchangeably. So it's really important that you understand it at a high level. Obviously, the object line is things we use to draw the objects with. The hidden line is usually dotted, and it's used to show things like over here, these holes in each of these parts. As the name suggests, a dimension line is used to dimension the various dimensions of the part. A leader line can sometimes be used for dimensioning, but also can be used as a labeler or for explaining specific details of the part. The center line is important to show that you are clearly identifying the center of things like, in this case, a cylindrical object, or with the crosshairs over here. In terms of the break line, I don't have one on this image, but it has a nice supportive role. If you can imagine, let's say that this blue piece was, say, instead of 1.5 inches long, perhaps it was 10 feet long, which is ridiculous. And if we tried to draw that, we'd definitely run out of paper, or we'd have to scale this whole part very awkwardly on this sheet of paper. So you would basically draw this break line on the part and then label it as whatever, however many feet you wanted it to be, to show that, you know, it's not that length, but it reflects the correct dimension. And then the cutting plane lines are used for if you were to cross section a part through the middle of it, what would the features look like if you were, say, a viewer inside the part? And that's what these kind of cutting plane lines or viewing plane lines can help you with. So here we have a slightly more complex blueprint from Kennametal in regards to another one of their 4-inch Kenlock milling cutters. And the content of this blueprint is a little bit outside the scope of what I'm trying to teach here, but I just want to raise your awareness or maybe even appreciation for some of the more advanced, more complex blueprints. And here, this print reflects more multi-component assemblies and also something known as geometric dimensioning and tolerancing. So as you can see over here, by the balloons, we have a few more components reflected in this total assembly. And here we have some more, and they're put together on this one cutting tool. I also want to raise your awareness to this one note over here. I'll highlight it in green where it says, for complete mounting specifications, see the drawing number as reflected here. And that's important because it shows that just this by itself isn't enough to use it correctly. You're going to have to refer to a different drawing or a different blueprint. Another awareness I want to raise is here by this hexagon G, and it shows that this dimension is produced when the cutter is rotating, and that's right over here. And so this is the angle that it creates. So it's important for the user to know they're going to use this cutting tool to machine something at this angle, and this is the product that'll get them there. Another thing I want to point out is this note over here on this dimension where it says you have this insert, which is actually the bit that cuts on the, it's actually the piece of the cutting tool that cuts metal reflected over here, but we need 5 of them. So just like this image to the right shows that this has, in this case, it has 6 cutting edges, and that this blueprint is showing that this particular cutter is going to need 5 of them. So they're not all shown on here, but it's up to the user to know that they are equally distributed around the circumference of the cutter. So obviously in this little workshop, it was not my intent to make anybody expert blueprint readers, but rather to just kind of raise the awareness to design and blueprints. And I know everybody likes to do innovative designs, but the process is incomplete if you cannot create the blueprints for that design or can read someone else's design, because and you read designs by way of blueprints. If you're going to manufacture something, blueprint gets extremely critical. So I strongly encourage those innovators and designers to deep dive, creating dimensions and ultimately blueprints. I wanted to raise awareness to some of the basic blueprint details, and I think we've hit on some key ones. And to build some beginning skills for reading and creating blueprints. Yeah, even if you take a major course in design and drafting and print creation, ultimately each manufacturer has their own specifications, and you end up learning on the job. So they have a lot of attention to details that are specific to their product. So that learning only comes by getting employed in those places and literally learn by doing so. And then finally, I just wanted to raise some appreciation for some of the advanced blueprint features, and we mentioned things like GD&T and so on, just so you know that there's more to it than just a basic dimension and a basic tolerance. And with that, I just want to wish everybody the best of luck and say thank you, and hope this little workshop was helpful to you. Take care.